Hello, grade 9. Welcome to your lesson on voltaic cells or batteries. We're calling this lesson portable energy. So let's get into it. What are batteries or voltaic cells? Well, batteries, what they do is they convert chemical energy into electrical energy. We've talked about this already, but what's happening is that there's energy stored within the chemicals of a battery. And that energy causes electrons to move from one terminal of the battery, the negative terminal, to the other terminal of the battery, the positive terminal. And the electrons really want to get from one side to the other, which means that they have a potential energy or difference that we call voltage. So electrons want to get from one side of the battery to the other because of chemical reactions that are happening inside of the battery. And as a result, energy is being converted from that chemical energy into electrical energy. Batteries are used like crazy. Worldwide, people buy over 15 billion batteries annually. And I know a lot of devices now come with rechargeable batteries inside of them. I'm assuming that still counts. But even the disposable batteries are still used just a ton. And boy, did they ever start for me getting used more once I had kids. I still go through double A's and triple A's like crazy. Silly triple A's. So tiny, but so expensive. Anyways, voltage can be generated, and this is the whole idea of how a voltaic cell or a battery works, by placing two different metals in a solution containing either a salt or an acid. Now, when I say containing a salt, that means any ionic compound. So you learned way back in chemistry that when I have a metal bonded with a nonmetal, I have an ionic compound. And when ionic compounds are dissolved in water, they are electrolytes, as are acids, which means they conduct electricity. This is important inside the battery because it provides what we call our internal circuit. It allows charge to move between the two terminals or electrodes of our voltaic cell. Anyways, when I have two different metals in solution, one metal is going to be losing electrons, which goes into the circuit, and the other metal is going to be gaining electrons, which would be the positive terminal of the voltaic cell. And again, those electrons, because they want to get from negative to positive, have a voltage. They have energy. And that's what we're using in a circuit that's powered by a battery. We can also call these devices electrochemical cells, which is kind of more of a blanket term than voltaic cell. And I mean, electro, right, has to do with both electrons and electricity, and then chemistry. But yeah, that's all that's happening is you have, well, it's actually not all that's happening. It's pretty complicated. You'll learn all about it in Chem 30. But at the end of the day, it has to do with the fact that we have two different metals in an electrolyte. And as a result, it ends up providing a voltage. We're going to get a little bit more into it. When we use the term battery, it actually has a specific meaning, but we don't use it in everyday life this way. What battery means is when we have more than one of these voltaic or electrochemical cells connected together in series. And the reason why we do that is to get a higher voltage. So if I take a look at this 9-volt battery, if you actually open up a 9-volt battery, what you have inside are all of these teeny tiny smaller batteries, 6 of them. Each one of those batteries is 1.5 volts. So because they're connected in series, so you can kind of see here that this is a negative terminal right here, that then goes down to a positive terminal. I would assume that this is connected like this, and this is a negative terminal, and then this is a positive terminal. Can't even see that, but it keeps on going, right? It's connected in series. And you can see that you have a connection here, and then underneath here you would have one, and underneath here you would have one, and it all connects together. That might be slightly wrong. It could actually be like this and then this and then this. Not that it matters. But at the end of the day, these are connected in series. And so as a result, all their voltages add together. That's the technical way to use the term battery, is that it's more than one voltaic cell connected in series. But we don't do that in everyday life, right? Like a AA voltaic cell is not really truly a battery because it's just one cell, but nobody's going like, yeah, that's a voltaic cell, right? And correcting people. You don't want to be that guy. Don't be that guy. Anyways, so going through again the parts, an electrochemical cell consists of two different metal electrodes surrounded by an electrolyte. And we talked about electrolytes already in chemistry, but an electrolyte is an ion-containing mixture that conducts electricity. So you need to have an electrolyte. And as it said on the last slide, that's either going to be a salt dissolved in water, which means an ionic compound, or an acid. Either one is going to be an electrolyte. It's going to have ions in solution. So this is a model of a very simple voltaic cell. This actually has a name when you have zinc and copper. It's called Daniel's cell. And it does a great job of producing a voltage. It's got two different metals, as we talked about on the last slide. It's got zinc and it's got copper. Each one is in an electrolyte solution, so likely copper 2 sulfate over here and zinc sulfate over here. And then we have in the middle something that's called a porous boundary, and specifically this is actually a salt bridge. All this does is it allows ions to move between the two electrodes, between the two solutions. Okay, that provides our internal circuit. It allows charge to move back and forth. If that didn't happen, charge would build up on one end of this voltaic cell and it wouldn't continue to work. So to go a little bit more into detail of what's happening here, and this is going past what you need to know, but I think it's still good for some of you to have a little bit of an understanding of how this works, because I know that helps you learn it. In this half cell, so this full thing is a voltaic cell, I'm looking at half of it. In this half cell, what's happening is zinc is losing its electrons to become Zn2 positive, so zinc ion, and it releases 2 electrons. These electrons end up going through the circuit, which in this case is just a light bulb. The zinc over time gets eaten away as more and more of the solid zinc turns to zinc ion and in the process releases electrons. This is called the anode. We'll talk more about that in a second. Over here we have copper. Copper is gaining electrons, so it goes through the circuit, it's going through, and then it meets up over here, right, at the copper end. So what's happening at the copper end is that I have the 2 electrons that are lost from the zinc meeting up with copper ions that are in this solution and making solid copper. So at this end, copper is actually being plated on this electrode, and over time it's going to get bigger as more and more copper collects on that electrode. This is called the cathode. So where metal gets plated and it gets bigger over time, that is the cathode. All right. I think we have some more information about that on the next slide. The last thing I'll say is that in order for electrons to keep on building up and negative charge to keep on building up here, in order for that not to happen, I need to have negative things traveling from this half cell to this half cell so that negatives don't build up over here. So what happens is negative ions, like the sulfate, are going to travel in this direction through the salt bridge. In the opposite direction, I'm going to have positive ions like the zinc ion traveling from here to the other end. And by doing that, the charge does not build up in either of the half cells, and it creates what we would call a complete circuit because the negative charge is going all the way around in a loop. So let's talk more about the electrolyte. An electrolyte is an ion-containing mixture that conducts electricity. That's the definition of electrolyte. It conducts electricity because ions are positively and negatively charged, and electrolytes contain these ions. That separation of charge will allow a current of electrons to move through the solution. So if you take a look, something like ethanol or alcohol, it has no conductivity. Why? Because it is molecular. It does not release ions when it's dissolved in water. However, if we have an ionic compound like potassium chloride, this will have conductivity because when it dissolves in water, it separates into its ions, and as a result, it conducts. Acetic acid, which you've learned about, that's vinegar, is a weak acid, which means it does not have as many ions as a strong acid or an ionic compound would. So because this is a weak acid, it is an electrolyte, but it's a weaker electrolyte than this ionic compound is. So a little bit more about terminology. You may have heard the term wet cell and dry cell, especially when it comes to auto batteries. What wet cells use is something wet, a liquid electrolyte. So car batteries, for example, contain sulfuric acid typically. So that would be a wet cell. Well, dry cells instead have a paste, plastic, or a ceramic solid electrolyte instead of having liquid that sloshes around. So when you take a look at something like a AA battery or a button cell battery or any of that, those would be dry cells. So dry cells, as it says on the left, are small. Electrolytes are moist solids. Oh, that moist word. There's no leaking of chemicals coming out of there. It's easy to handle. They're more expensive. They're difficult to manufacture, and they cannot withstand overcharging if they are rechargeable. Now, a wet cell is large. Electrolytes are liquid. Corrosive chemicals tend to leak out. If it's misused, it's difficult to handle. It's less expensive, very easy to manufacture, and it has the ability to withstand overcharging. I think you can see where the big benefit is here for automobiles. The overcharging thing is massive, right? Because your car battery is recharging all the time as it runs from the alternator. So having that ability to possibly overcharge is important. So if I take a look here, I've got a few kind of pictures of wet and dry cells. So this would be an example very similar to what we just saw on the previous page or 2 pages ago, copper and zinc. So this would be an example of a wet cell because I have a wet electrolyte inside, liquid electrolyte. Something like this looks kind of like a C or a D battery, but it's, yeah, actually it exactly is. The manganese dioxide kind of lets you know. So I have here a dry cell battery. So instead of having a liquid electrolyte, it has a paste. So it's still like wet-ish, but it's mainly made out of solid. It's not sloshing around like a liquid, so it's a paste instead of a bunch of undissolved solid in some liquid. So that's how something like that works, a dry cell battery. So in summary, wet cells have liquid electrolytes in them, while dry cells instead have something like a paste, a plastic, or a ceramic. Let's talk about the electrodes a little bit more. This gets into what I already talked about in terms of terminology. Electrodes are simply defined as solids that will conduct electricity. An electrochemical cell has 2 electrodes. It has the anode, which is losing electrons. Okay, so anode is losing electrons. There are ways to learn this, but they get a little bit complicated as time goes on. The big thing that I want you to think of is the fact that in the word anode, I have this N. And I want you to think of that N as meaning negative. This is the negative terminal of the battery. And you know that electrons are negative. So this is where electrons are coming out of, is from the anode. Later on in Chemistry 30, you're going to learn some more specific terms around this that are helpful. But for now, we're just going to go with this. Anode is negative, the negative terminal, and that's where electrons are coming out of. When I look at the cathode, this T, I want you to think of as the positive sign. Okay, it's the positive terminal of the battery, and this is where electrons are going to. Okay, so this is where electrons are traveling to, is that positive terminal. And electrons are very smart. They travel alphabetically from A to C. So electrons are going from anode to cathode because they know their ABCs. That's the other trick. So taking a look at this. Oh, and now all my ink is in the way. You're seeing a little bit of what we just talked about. So I have my aluminum anode, which electrons are leaving from. They then go through the circuit to the positive cathode, which is copper in this case. You don't have to know why aluminum is the anode and why copper is the cathode. We're not at that point. Okay, you just have to know that when I tell you it's the anode, or if I show you the direction of electrons, you can figure out which is which. Okay, almost done here. This we've talked about before. It's been in previous notes. But if you want to increase the voltage of voltaic cells in order to get more voltage out of it, what you do is you attach the batteries in series. And I kind of almost think about this as like those Hot Wheels car launchers that like have the wheel with the motor, goes and it makes the car go further. Well, imagine you have a bunch of those in a row. Well, the car is going to end up going really fast, right? As it gets boosted by all of the car booster things. So in the same way, when I have batteries connected, or voltaic cells, maybe I should say instead, connected in series, each one adds to the energy of the electrons. Okay, so connected in series, it's like, oh, 1.5 volts, and another 1.5 volts, and another 1.5 volts, and another 1.5 volts, and you got 6 volts total. Well, in a parallel arrangement, it's just a straight up 1.5 volts because they're not adding ends to ends. So this system here will last longer because it has 4 batteries to draw the electrons from instead of just 1, but it's not adding to the voltage. In comparison, the same electrons are going through all 4 of these batteries, but it's building up the energy. So this gives a higher voltage, but of course it's not going to last as long. So this is important because most cells do not produce more than 2 volts. Some with lithium and stuff get over 3 volts, but most don't get to 2. So in order for us to get higher voltages, we have to connect several cells together in a series to get that. So even something like a laptop, when it has like a 9-volt battery or whatever, that's actually a result of, or 12, I can't remember what it is for a laptop if I'm being honest, but that's a result of several cells being connected in series in order for that to happen. So again, when we have it in series, voltage is going to add together. So you tell me, if I add this system, 1.2, 1.2, 1.2 in series, what would be the overall voltage of that cell system? Yep, 3.6 volts. And if I instead had it in parallel, 1.2, 1.2, 1.2, you'll tell me what would be the voltage of that parallel battery system. And the answer is 1.2 volts, but it's going to last a bit longer. That's why devices might have batteries that are connected in parallel, is because they need to last for a longer time. All right, that's it. That is your lesson on voltaic cells and batteries. So, oh, no, wait, there's one more slide. I forgot about this. One more piece of terminology. Primary cell versus secondary cell. Primary cells cannot be recharged. They're one-time use. So your typical AA battery, that would be a primary cell. Once it's done, it's done. Once the chemicals are used up, it's over. Secondary cells can be recharged. The chemical reactions can be reversed by applying a voltage in the opposite direction. So when you plug in something that's rechargeable, the current is actually flowing the opposite way, which causes the opposite chemical reactions to occur. It's storing up the chemical energy again. So when something is charging, it's actually doing the conversion of electrical to chemical energy during that time. Electrical to chemical. Instead of the normal chemical to electrical. And it's building up reactants again, so it can repeat the reaction for the battery to function. So that's a secondary cell. Secondary cells can be recharged, while primary cells cannot. So what did you learn through all this? Well, you learned a bunch of terminology. You should know what voltaic cell is, electrochemical cell, and battery. You should understand that voltaic cells convert chemical energy to electrical energy. You should know that it has a electrolyte, which conducts electricity because it has ions. You should know what an electrode is, that it's two different metals. You should know anode versus cathode and how that works, and which way the electrons flow. You should know about wet cells versus dry cells and primary versus secondary cells as well. All right, that's it. Have a good rest of your day.